Reality itself is not what it seems. We are about to explore 25 cosmic paradoxes that challenge everything we think we know. These are not simple riddles, but profound contradictions at the very heart of physics. They force us to question the flow of time, the nature of nothingness, and the role of our own observation. By the end of this journey, you will see the universe through a completely new and startling lens. We will uncover how watching a particle can rewrite its history, and why the silence of the cosmos might be its loudest message. What part of your reality are you most certain is true? Two identical twins stand together, a perfect mirror of shared life and time. One remains on our familiar planet, while the other boards a spacecraft capable of traveling at a staggering fraction of the speed of light. Their destination is a star many light-years away, a journey that will take years from the perspective of those watching from home. Yet when the ship finally returns, landing once more on Earth, the impossible has happened. The twin who ventured out steps onto the tarmac, still youthful, while the sibling who stayed behind has aged decades. Their shared timeline has been torn in two. This is the twin paradox, a thought experiment that emerges directly from Einstein's theory of special relativity. It demonstrates a concept called time dilation, the idea that time itself is not a constant river flowing at the same rate for everyone. Instead, it is more like a personal stream, and the speed of your journey changes its current. The faster you move through space, the slower you move through time. For the astronaut twin, racing through the cosmos at near light speed, every second ticked by more slowly than it did for the sibling living a normal, stationary life on Earth. This shatters the Newtonian view of a single, universal clock governing the cosmos. There is no master ticker, no background metronome against which all events are measured. The passage of time is a deeply personal experience woven into your state of motion. So how can two people starting from the same moment end up in such different temporal places? The answer lies not in the twins themselves, but in the very fabric of the universe they are moving through. Yet this bending of time is not the only profound silence in the cosmos. Decades ago, the brilliant physicist Enrico Fermi sat down to lunch with colleagues, discussing the high probability of life on other worlds. Amid the chatter, he posed a deceptively simple question that has echoed through the decades. Where is everybody? The universe is unimaginably vast and ancient, filled with hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets orbiting within habitable zones, worlds where the conditions for life as we know it could exist. The numbers alone suggest a cosmic metropolis, a universe teeming with civilizations. Yet when we point our most powerful telescopes to the sky and listen with our most sensitive radio dishes, we are met with an unnerving and absolute quiet. This is the Fermi Paradox, a stark contradiction between the high probability of alien life and the profound lack of any evidence for it. One compelling resolution is known as the Great Filter. This idea suggests that at some point between the emergence of simple life and the rise of a galaxy-spanning civilization, a barrier appears. It could be an evolutionary step that is almost impossible to cross, or perhaps a technological trap that every advanced culture eventually falls into, such as self-annihilation through war or environmental collapse. The filter acts as a cosmic sieve, and its terrifying implication is that we might be on one side of it, destined to fail, or have already miraculously passed through it alone. Another, more peaceful idea is the zoo hypothesis. What if other civilizations are out there, but they have chosen to observe us from a distance, like naturalists watching animals in a vast galactic preserve. They remain silent to avoid interfering with our development, leaving us in a state of cosmic isolation until we are mature enough to join the interstellar community. This paradox forces a deep and humbling self-reflection. Is intelligence a rare and precious fluke in the universe, a single spark in an endless night? Or is it a fleeting phase, a brief candle that burns brightly only to be snuffed out just as quickly? The silence we hear may not be empty. It might be the most important message we will ever receive, a warning whispered across the light years. This deep cosmic silence about other life forms stands in stark contrast to the deafening noise of a logical impossibility. What if you could go back and change a single, pivotal event in your own past? The grandfather paradox places you in that very scenario. You step into a time machine and journey back to an era before your parents were born. Your mission is simple: to prevent your grandfather from ever meeting your grandmother. Perhaps you redirect him on his way to a dance, or you intercept a crucial letter. You succeed. Because of your actions, your grandparents never marry, and your father is never born. This means you, the time traveler, are never conceived. So here is the impossible question. If you were never born, who traveled back in time to set these events in motion? The entire sequence collapses into a loop of pure logical nonsense. This paradox is more than a puzzle. It is a fundamental challenge to the idea of traveling into a single, unchanging past. It exposes a deep flaw in our intuitive understanding of cause and effect, suggesting that the universe simply cannot permit such a violation of its own internal logic without breaking. So how could time travel to the past ever be possible? Physicists have proposed fascinating ways out of this trap. One idea is the Novikov self-consistency principle. This principle suggests that the timeline is rigid and unchangeable. Any actions you take in the past were always a part of that past. You might think you are changing history, but you are actually just fulfilling it. Your attempt to stop your grandfather was always the very reason he met your grandmother in the first place. Your presence in the past is a closed loop with no beginning and no end. Another, even more mind-bending solution comes from the many worlds interpretation of quantum mechanics. In this view, your time travel journey does not take you back into your own past. Instead, the moment you arrive, you branch off into a new, parallel universe, a separate timeline entirely. In that new reality, you might indeed prevent that version of your grandfather from starting his family. You would never be born in that new branch, but your existence in your original timeline remains completely untouched. This paradox forces us to confront the nature of our own choices. Do we possess true free will, the power to alter the flow of events, or are our actions, even those made with a time machine, merely playing out a script that was written long ago? The answer might redefine our place in the cosmos. But this strange link between observation and reality is not confined to the microscopic world. It reaches out with bizarre consequences into a place we can all understand, a simple box containing a cat. This thought experiment, devised by physicist Erwin Schrödinger, was meant to showcase the sheer absurdity of applying quantum rules to everyday objects. Imagine a steel box completely sealed from the outside. Inside is a living cat. Also in the box is a single radioactive atom, a Geiger counter to detect its decay, and a vial of deadly poison. The mechanism is cruel in its simplicity. If the radioactive atom decays, the Geiger counter will click, triggering a hammer that shatters the vial, releasing the poison and killing the cat. Now here is where our normal logic completely breaks down. According to the rules of quantum mechanics, that single radioactive atom does not have a definite state. Until someone measures it, it exists in a superposition. It is both decayed and not decayed at the same time. But if the atom is in both states, then the entire chain of events is also in both states. The Geiger counter has both clicked and not clicked. The hammer has both fallen and remained still. The poison has both been released and remained sealed. Therefore, the cat must be both alive and dead. It is only when you, the observer, finally open the box and look inside that this ghostly superposition collapses into a single, definite reality. You see the cat either alive or dead, but not both. Schrödinger intended this as a critique, a way to show how ridiculous the quantum interpretation seemed. Yet the paradox stuck, forcing a profound question. What does it mean for something to be real? Is reality something that exists independently out there, waiting to be discovered? Or is our act of looking, our consciousness, somehow required to pin it down, to force the universe to make up its mind? This blurs the very line between the world of tiny atoms and our own solid, macroscopic experience. It suggests that the simple act of seeing might be the most powerful force in the cosmos. The unsettling idea that observation defines reality collides with a far more destructive force, a place where information itself seems to vanish forever. At the edge of a black hole lies the event horizon, a point of no return. Anything that crosses this boundary, whether a single particle or an entire star, is lost to the outside universe. The black hole consumes it all, leaving behind only three simple properties: its mass, its electric charge, and its spin. This is what general relativity tells us. Everything else, all the intricate information that made up the fallen object, its composition, its structure, the story of its existence, appears to be permanently erased from the cosmos. This presents no problem for Einstein's theory of gravity, which sees space and time as a smooth, continuous fabric, but for quantum mechanics, this is a catastrophe. The fundamental rules of the quantum world state that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. This is the bedrock of a deterministic universe where the past always leaves a trace. Then Stephen Hawking made a stunning discovery. He realized that black holes are not entirely black. Due to weird quantum effects at the very edge of the event horizon, they slowly leak a faint glow of radiation. This Hawking radiation is thermal, like the heat from a stove. It is random noise carrying no information whatsoever about what fell inside. Over billions of years, this process causes the black hole to evaporate, shrinking until it finally vanishes in a final puff of energy. And here lies the paradox. If the black hole evaporates into pure, featureless radiation, then all the information about everything it ever consumed is irretrievably lost. The universe would have no memory of what fell in, violating a core principle of quantum physics. This creates a direct conflict between our two most successful theories of reality. One potential solution is as beautiful as it is strange, the holographic principle. This idea suggests that all the information about the three-dimensional volume inside a black hole is not lost, but is instead perfectly encoded like a cosmic hologram on its two-dimensional surface, the event horizon. The information is preserved there, imprinted on the fabric of spacetime itself, and is slowly released back into the universe in a scrambled form as the black hole evaporates. Yet, how this encoding and retrieval actually works remains one of the greatest unsolved mysteries in physics. This paradox forces a profound question about the nature of our reality. Is the universe fundamentally predictable? A system where every event is locked into a chain of cause and effect that can, in theory, be traced backward? Or can information truly be erased, introducing an element of fundamental randomness into the cosmos? The battle to solve the black hole information paradox is the primary driving force behind the quest for a theory of everything, a single framework that can finally unite the world of the very large with the world of the very small. A book sits on a table, its cover embossed with the title Hamlet. You pick it up feeling the weight of its profound ideas, a masterpiece that defined literature. Now picture a time traveler, a fan of the Bard, who takes a printed copy of Shakespeare's complete works back to 16th century England. She finds a young, struggling William Shakespeare and hands him the book, hoping to inspire him. He reads it, is astonished by the brilliance of the words, and proceeds to publish them under his own name, becoming the legendary playwright we know today. This is the Bootstrap Paradox, a loop of cause and effect with no beginning. Who truly wrote those plays? The information, the very text itself, did not spring from Shakespeare's mind, nor did it come from the time traveler who merely possessed a copy of his work. It exists in a perfect, maddening circle, an object or idea that has no discernible origin. It was never created, it just is. This paradox violently wrenches apart our most basic understanding of causality, the principle that every effect must have a cause. We are comfortable with chains of events, a domino fall stretching back to a first push. But what happens when the dominoes form a circle with no first and no last? The Bootstrap Paradox suggests that some things in the universe might not have a first cause at all. They are simply self-existing loops. This is not merely a clever science fiction trope. It strikes at the heart of a deterministic universe, one where every event is predetermined by what came before. How can you have determinism if the chain of events has no starting point? The loop itself becomes the only reason for its own existence, a cosmic Ouroboros, the snake eating its own tail. This naturally loops us into one of the most profound questions we can ask. If a simple book of plays can exist without a creator, what does that imply for the vastly more complex universe around us? Does the cosmos itself require an original cause, a first mover, or could it too be a bootstrap paradox on the grandest possible scale, a self-contained loop of existence with no beginning and no end? The unsettling possibility that our universe is a self-contained loop echoes another, even more personal doubt about the nature of existence itself. What if the cosmos we perceive is not the ultimate foundation, but merely one layer in a vast digital reality? This is the simulation paradox, a modern philosophical dilemma that questions the very ground beneath our feet. The argument, famously developed by Nick Bostrom, begins with a simple, staggering premise. If it is ever possible for a highly advanced civilization to create incredibly realistic simulations of reality, complete with conscious minds that believe they are real, then the number of simulated beings would eventually come to vastly outnumber the beings in the original, base reality. Just think of the sheer computational power a truly advanced society might possess. They could run not just one, but millions or even billions of such simulations, each with its own rich history and sentient inhabitants. Now, from our perspective, we are faced with a simple statistical probability. Given that there would be so many more simulated minds than real ones, it is far more likely that we ourselves are among the simulated, not the original. This is not a claim that we are in a simulation, but a stark assessment of the odds. The implications ripple through everything we think we know. The fundamental laws of physics we dedicate our lives to studying, from the speed of light to the force of gravity, would not be the bedrock laws of the universe. They would simply be the local programming rules of the simulation we inhabit, the underlying code of our existence. This forces a profound crisis for empirical science. For centuries, we have operated on the faith that by observing the natural world, we are uncovering deep, objective truths about reality. But if we are in a simulation, are we truly discovering the universe, or are we merely reverse engineering the software written by our potential creators? Every experiment, every observation becomes an act of debugging rather than discovery. This paradox ultimately forces us to question the nature of our own perception. What is the difference between a simulated consciousness that feels real and a base reality consciousness? If every memory, every emotion, and every sensation is just data in a program, then what, if anything, makes our experience of truth authentic? The world you see and feel may be nothing more than an elegant and utterly convincing user interface. Our reality could be an impossibly rare accident, a fleeting moment of order in an endless sea of chaos. This is the paradox that emerges when we follow the grim prophecy of the second law of thermodynamics to its ultimate conclusion. The universe, like a wound-up clock, is slowly but surely running down. Energy is spreading out, differences in temperature are evening out, and everything is moving toward a state of maximum disorder, a final state known as entropy. One day, in the far, far future, the cosmos will reach a uniform, lukewarm temperature. Stars will have burned out, black holes will have evaporated, and no work will be possible anywhere. This is the heat death of the universe, the ultimate end of all activity and change. It is the most probable state for the cosmos, a featureless, silent equilibrium. Yet here we are, living in a universe brimming with structure, from the intricate swirl of galaxies to the delicate machinery of a single cell. Our existence is a monument to improbability, a defiant pocket of low entropy in a cosmos destined for high entropy. This leads to a bizarre and unsettling possibility. In a universe that is either infinitely old or infinitely large, the random jostling of particles will eventually, through sheer chance, create any possible configuration, no matter how unlikely. Given enough time, a fully formed, self-aware brain could simply fluctuate into existence out of the void, complete with a lifetime of false memories, believing it is a person living in a real world. Physicists call such an apparition a Boltzmann brain. And here is the terrifying statistical truth. It is infinitely more probable for a single, disembodied brain to randomly assemble than for an entire, ordered, 13.8 billion-year-old universe to come into being. So why are we here, embedded in a vast, coherent cosmos with a seemingly consistent history? Why are we not just momentary flickers of consciousness, isolated Boltzmann brains hallucinating a reality that does not exist? This paradox forces us to question the very arrow of time and the reliability of our own memories. Is our past, with its galaxies and dinosaurs and civilizations, a real linear progression from a low entropy beginning? Or is our present order just a temporary, random fluctuation in an otherwise dead cosmos, and our perception of a structured past merely an illusion conjured up by chance? We are left wondering if we are legitimate residents of a cosmic story, or just phantoms in the void, dreaming of a universe for a single, fleeting instant. Our own planet, our bodies, and every star we see are made of the same ordinary atoms. Yet this familiar stuff, the very matter we have studied for centuries, is nothing more than a cosmic afterthought, a mere 5% of the total content of the universe. The overwhelming majority of the cosmos is made of two profound and invisible mysteries, dark matter and dark energy. We cannot see them, touch them, or directly detect them with any instrument we have ever built. Their existence is known only through their ghostly grip on the universe we can see. Dark matter acts as a cosmic scaffold. We know it is there because galaxies spin so fast that they should fly apart, yet something's immense gravitational pull holds them together. It is an invisible glue binding the cosmos on the largest scales. Dark energy is even more strange and dominant. It is a repulsive force woven into the fabric of empty space itself, causing the expansion of the universe to accelerate at an ever-increasing rate. It is not pulling things together, but relentlessly pushing them apart. The paradox is staggering. Over 95% of reality is composed of entities that are completely unknown to us. We are like actors on a stage performing our lives, utterly unaware of the vast, hidden machinery that controls the set, the lights, and the very dimensions of the theater itself. This shatters a foundational idea in science, the Copernican principle, which taught us that we do not occupy a special place in the universe. In a bitter twist, it turns out we are made of special stuff. The atoms that form everything we know and are the exotic exception in a cosmos dominated by darkness. This forces a humbling realization. Our entire understanding of physics is based on studying the 5%. It is as if we spent our whole lives studying the ripples on the surface of the ocean, completely oblivious to the dark, crushing depths beneath. What is the true nature of this dark cosmos? Is dark matter a sea of undiscovered particles, or does it require a fundamental rewrite of the laws of gravity? Is dark energy a constant property of the vacuum, or is it a dynamic field that could one day tear the universe apart? We are left staring into a profound abyss, a universe where the rules are written in a language we have only just begun to suspect exists. This strange power of observation finds its ultimate expression in a phenomenon so counterintuitive it seems to defy motion itself. An unstable particle sits poised on the edge of decay, ready to transform into something new. Left to its own devices, it will inevitably change. But if you watch it, if you continuously measure it to see if it has decayed, something remarkable happens. It never does. Your constant gaze pins the particle in place like a butterfly under glass. This is the quantum Zeno effect. Each time you check on the system, you force its fuzzy, probabilistic wave function to collapse back to its starting point. It is as if you are asking a child, "Are we there yet?" over and over on a long car ride. The relentless questioning resets the journey, preventing arrival. The effect gets its name from an ancient Greek philosopher, Zeno, who argued that a flying arrow is actually motionless. At any single, frozen instant in time, the arrow occupies one specific point in space. If time is just a collection of such instants, then when does the motion actually happen? The quantum version of this paradox suggests that reality at the smallest scales is not a smooth, continuous movie, but more like a series of individual frames. Our conscious observation, our act of measurement, is what clicks the projector forward from one still image to the next. Without that engagement, the universe might simply be a vast collection of possibilities, a reel of film waiting for a viewer. This blurs the line between the observer and the observed so completely that they become a single, intertwined system. We are not passive witnesses to a universe unfolding on its own. Our very attention is a creative force, actively participating in shaping what is real. How can something as simple as looking hold such power? This question strikes at the very heart of the measurement problem, the greatest unresolved issue in quantum mechanics. What, in the end, truly qualifies as a measurement? Is it the click of a machine, the note in a logbook, or the flicker of awareness in a conscious mind? The answer remains hidden, suggesting that our role in the cosmos may be far more active and far more strange than we ever dared to believe. Yet the universe we see is not a static, infinite gallery of light. Step outside on a clear, moonless night and look up. The sky is not a blinding, solid sheet of brilliance. It is a deep, velvety black, punctuated by the faint, lonely pinpricks of individual stars. This simple, everyday fact, the profound darkness between the stars, is one of the most significant clues we have about the true nature of the cosmos. It is known as Olbers Paradox, named for the astronomer who popularized it in the 19th century. The puzzle is this: if the universe is infinite, unchanging, and filled uniformly with stars, then every single direction you look, every line of sight stretching out into the depths of space, should eventually land on the surface of a star. There would be no gaps, no darkness. The entire night sky would glow with the combined light of every sun in existence, blazing as brightly as our own sun does at noon. The fact that it does not, that we stand beneath a canopy of black, tells us that at least one of our initial assumptions is catastrophically wrong. The universe is not infinite in the way we imagined, or it is not static, or it is not infinitely old. The resolution to this paradox lies in the dynamic nature of the cosmos itself. The universe has a finite age, roughly 13.8 billion years. This means the light from the most distant stars simply has not had enough time to reach us yet. We are surrounded by a cosmic horizon, a limit to how far we can see, not because our telescopes are weak, but because the universe has not existed long enough for light from beyond that point to travel to our eyes. Furthermore, the universe is expanding. This expansion stretches the very fabric of space, which in turn stretches the light waves traveling through it. This effect, called redshift, shifts the visible light from the most distant galaxies into the invisible infrared part of the spectrum, draining their energy and making them too faint for our eyes to perceive. The darkness of the night sky, a fact so basic a child can observe it, is not an absence of evidence. It is the evidence. It is the signature of a cosmos with a definite beginning, a universe that is flying apart, evolving, and telling a story that is still unfolding. This simple observation, made centuries ago, contained the seeds of the Big Bang theory. It reminds us that the most profound truths are often hidden in plain sight, waiting for us to ask the right, simple question. What if the void itself is the message? Einstein himself was deeply troubled by the implications of quantum theory. He, along with colleagues Boris Podolsky and Nathan Rosen, crafted a brilliant thought experiment designed to expose what they saw as a fatal flaw. Imagine a single particle decaying into two smaller particles. These two offspring fly apart in opposite directions, traveling across the cosmos until they are light years apart. According to quantum mechanics, these particles are entangled. Their properties, like their spin, are not defined individually but are part of a shared, unified state. They exist in a coupled superposition, a single quantum description linking them across the vast emptiness. Now, a scientist on a distant space station measures the spin of one particle. At that exact instant, the spin of its twin, millions of light years away, becomes certain. It is as if the measurement here sends an immediate command to the particle there, forcing it to choose a state. This seems to violate the universe's ultimate speed limit, the speed of light, the cornerstone of Einstein's own theory of relativity. No signal, no information, no influence of any kind should be able to travel faster than light. Yet here, the correlation appears to be instantaneous. Einstein dismissed this bizarre connection as spooky action at a distance, believing it proved that quantum mechanics was an incomplete theory, that there must be some hidden variables, some deeper, unseen properties that predetermine the particles' states from the moment they were created. For decades, this was a philosophical debate. Then a physicist named John Bell devised a way to test it. Real-world experiments have since been conducted, and the results are unequivocal. The spooky action is real. There are no hidden local variables. The universe truly does permit this instantaneous correlation. This is the EPR paradox, and its resolution is more shocking than Einstein could have imagined. The particles are not communicating, they are not sending signals, they are, in a very real sense, not two separate entities at all. Their connection transcends the space between them, suggesting that separation itself might be an illusion, an artifact of our limited perception. The universe at its most fundamental level is profoundly non-local. What we perceive as empty space is not a barrier but a medium for a deeper, invisible wholeness. This interconnectedness forces us to abandon the classical idea of objects existing in isolated independence. We are left with a cosmos that is woven together into a single, inseparable tapestry, where observing one thread can instantly change the pattern of another, no matter how far apart they seem to be. The same fundamental laws that govern a planet's orbit would look perfectly normal if you ran the film in reverse. A planet circling its star backward still obeys every rule of physics. So why does our experience of time feel so different? We watch an egg fall from a table and shatter on the floor, a messy, irreversible event. We never see the fragments spontaneously gather, leap upward, and reassemble into a perfect egg on the table's edge. We remember yesterday with clarity, but the future remains a complete mystery. This is the arrow of time paradox, the stark contradiction between the time symmetry of physics and our one-way journey from past to future. The culprit is not found in the laws of motion or electromagnetism, but in the statistical tendency of the universe toward disorder, a concept we call entropy. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. It is this law that gives time its arrow. An egg is a highly ordered, low-entropy system. When it shatters, its molecules move into a more numerous set of disordered, high-entropy states. It is statistically possible for all those molecules to randomly jiggle back into the shape of an egg, but the odds are so astronomically low that it will never happen in the lifetime of the universe. Our forward-moving time is not a property of the individual particles, but of the overwhelming probability of their collective arrangements. The deep paradox is that the underlying laws governing those particles are completely blind to this direction. They work just as well forward as backward. So where did this arrow come from? The answer seems to lie in the very first moment of existence. The Big Bang must have been a state of incredibly low entropy, a supremely ordered and special starting point. Like a clock that was wound up just once at the beginning, the universe has been slowly unwinding ever since, and the increase of entropy is the ticking of that clock. All the order we see, from galaxies to life itself, is a temporary eddy in this vast, one-way river flowing from order to disorder. This forces a question that goes far beyond physics. Why did the universe begin in such an improbably tidy state? What set the cosmic clock ticking in the first place? The arrow of time may not be a fundamental feature of reality, but a ghostly emergent property, a memory of a singular and mysterious beginning. Empty space is not truly empty. According to our best understanding of quantum physics, the vacuum is a seething, bubbling sea of virtual particles. These are pairs of particles and antiparticles that spontaneously flicker into and out of existence, borrowing energy from the void for a fleeting moment before annihilating each other and vanishing. This quantum froth should be bursting with an unimaginable density of energy, a force pushing outward from the nothingness itself. This is the vacuum energy, a concept woven into the very fabric of quantum field theory. The math is clear and the prediction is staggering. The energy contained in a single cubic centimeter of this so-called empty space should be powerful enough to tear the entire observable universe to shreds in an instant. The number is so colossal it defies comprehension. a one with 120 zeros after it. Yet when we look out at the cosmos and measure the actual energy driving the universe's accelerated expansion, we find a value that is almost nothing. Not a powerful roar, but the faintest of whispers. The difference between the prediction and reality is the largest discrepancy in the entire history of science. It is not just a little wrong, it is wrong by a factor of 10 to the power of 120. This is the vacuum catastrophe, a paradox that reveals a terrifying chasm in our understanding of nothing at all. Why is the energy of the vacuum so close to zero when our theories scream that it should be unimaginably vast? This is not just a mathematical error. It is a fine-tuning problem of cosmic proportions. It suggests that something, some unknown principle or mechanism, is acting with unbelievable precision to cancel out nearly all of this vacuum energy, leaving behind only the tiniest remnant we can detect. What could possibly be so perfectly balanced? Is there a hidden symmetry in the laws of physics, a cosmic counterweight that we have not yet discovered? Or does this mean our entire theoretical framework for the quantum world is fundamentally broken when applied to the scale of the cosmos? The vacuum catastrophe forces us to confront the nature of nothingness itself. The empty space between stars, the void we once thought was simple and inert, may hold the deepest secret of all, a secret about why our universe is so improbably and so perfectly calm. Even the vacuum of space holds a different reality for everyone. Picture two astronauts floating in what seems to be the same perfectly empty void. One drifts peacefully, feeling nothing but the cold, silent emptiness around them. The other fires their rocket thrusters, accelerating faster and faster. For this astronaut, something miraculous and strange occurs. Their empty space is no longer empty. Their instruments suddenly detect a warm bath of particles, a gentle heat emanating from the void itself. This is the Unruh Effect. The very act of acceleration conjures particles from nothingness, warming the astronaut in their own private reality. Yet for their companion drifting inertially just a short distance away, the void remains utterly black, cold, and empty. They are sharing the same coordinates in space-time, but they are experiencing two completely different universes. How can this be possible? The key lies in a strange boundary that forms only for the accelerating observer, something called a Rindler horizon. As they accelerate, an invisible wall appears behind them, a point of no return that forever cuts them off from information in a part of the universe. It is analogous to the event horizon of a black hole, a boundary beyond which signals can never reach them. This horizon fundamentally changes their perception of the quantum fields that fill all of space. What the inertial observer sees as a calm, undisturbed field, the accelerating observer perceives as a bubbling sea of real particles, their existence made possible by the presence of this new horizon. This leads to a staggering conclusion. A particle is not an objective thing. It is not a tiny, independent marble you can point to. Its existence is entirely dependent on the observer's state of motion. There is no such thing as an absolute vacuum, a single state of true nothingness that everyone can agree on. Your reality is literally defined by your journey. This provides a stunning analogy for how Hawking radiation works at the edge of a black hole. Just as an accelerating astronaut sees particles because of their Rindler horizon, a black hole creates particles because of its event horizon. In both cases, a horizon makes particles real. This paradox forces us to abandon the last vestiges of a detached, objective cosmos. The universe does not present a single, fixed stage for us to observe. What we call reality is a deeply personal experience, a story told by the specific path we take through the fabric of space-time. Are the stars and galaxies we see simply the artifacts of our own particular trajectory? If we had chosen a different path, would we be surrounded by an entirely different cosmos? This bizarre dependency of reality on your own path now forces a question about the most personal journey of all, your own continued existence. A volunteer steps forward and places their head against the barrel of a strange new device. It is not a normal gun. This is a quantum suicide machine rigged to a radioactive source. When the trigger is pulled, the fate of the volunteer hinges on a single, completely random quantum event, like the decay of one atom. There is a 50% chance the gun will fire, and a 50% chance it will click harmlessly. According to the many worlds interpretation, the universe splits at that moment. In one branch, the gun fires and the story ends. In the other, it clicks and the volunteer lives. Now, imagine the trigger is pulled again and again and again. From the perspective of anyone watching, this is a brutal experiment. They will quickly see the volunteer die in roughly half of all branches. But from the volunteer's own first-person point of view, something incredible happens. They will only ever experience the outcomes where the gun clicks. They hear nothing but an empty click again and again. No matter how many times the experiment is repeated, from their subjective vantage point, they always survive. This is the thought experiment of quantum immortality. You are not witnessing a miracle. You are simply trapped within the narrow slice of reality where you continue to be conscious. Your personal timeline is not a single thread, but a path you are walking through a near-infinite multiverse, a path that, by its very nature, only includes the moments where you are alive to experience it. This creates a profound and unsettling sensation. From the inside, it feels like immortality. This forces a radical rethink of probability and identity. Is a 1 in a million chance of death truly a risk for you, if you will only ever find yourself in a universe where the 1,000,000 to 1 odds came up in your favor? Your consciousness seems to be a process that selectively tunes itself to the branches of reality where it persists. So who are you, really? Are you the specific collection of atoms that could have died in a lab? Or are you the timeless locus of experience that seemingly cannot die? This paradox pushes the very boundaries of what it means to be a self, suggesting that our sense of a single, continuous identity might be the greatest illusion of all. Our own continued existence is a statistical miracle on a cosmic scale. Every single thing you see, from the screen in front of you to the very atoms of your body, should not be here. The Big Bang was a furnace of pure, unimaginable energy, and that energy, according to our most fundamental laws of physics, should have condensed into perfectly equal amounts of matter and antimatter. For every particle of matter created, a mirror image antiparticle should have been born alongside it. Matter and antimatter are perfect opposites in almost every way, and when they meet, they annihilate each other in a flash of light, returning to the pure energy from which they came. The entire universe should have been a brief, brilliant flash, a sea of mutual destruction leaving behind nothing but a fading, featureless glow of radiation. There should be no planets, no stars, and certainly no one to wonder about their absence. Yet here we are. This is the Baryon Asymmetry Paradox, and it asks the most profound question of all. Why is there something, specifically matter, rather than nothing? The only possible answer is that the initial symmetry was broken. Somehow, for every billion pairs of matter and antimatter that annihilated in the early cosmos, a single particle of matter was left over. 1 in a billion survived the Great Annihilation. All the galaxies, all the stars, every living thing is made from that 1 in a billion relic. We are the leftover dust from a near-perfect cancellation. Physicists have identified a potential culprit, a subtle crack in the mirror symmetry of the universe known as CP violation. This is a tiny bias in the laws of physics that treats matter slightly differently from antimatter. It is like a coin that is perfectly forged, but when flipped, has a barely perceptible tendency to land on heads rather than tails. The problem is when we measure this CP violation in laboratory experiments, the bias is far, far too small. It is not 1 in a billion. It is more like 1 in a trillion or even less. The slight asymmetry we have found is utterly insufficient to account for the vast abundance of matter we see in the cosmos today. So where did the rest of the imbalance come from? This question haunts modern physics. There must be a source of CP violation we have not yet discovered, a fundamental process from the first moments of time that tipped the scales decisively in favor of matter. Perhaps it involves exotic particles that faded from existence a fraction of a second after the Big Bang. Or maybe it requires a deeper understanding of the forces that shaped the infant universe. We are left with a humbling realization. Our entire material reality, everything we are and know, depends on a tiny, unexplained anomaly in the first instance of creation. We are not the inevitable product of cosmic laws. We are the result of a single, fragile exception to the rule. This uniformity stretches across the entire sky, a perfect thermal blanket draped over the cosmos. We see it in the cosmic microwave background radiation, the faint afterglow of the Big Bang itself. This ancient light reveals a universe that is smooth to an astonishing degree, with a temperature that is virtually identical in every direction we look. The variations are minuscule, only about 1 part in 100,000. This seems natural until you realize the sheer scale of the problem. Consider 2 points on opposite sides of the observable universe. Today, they are separated by tens of billions of light years. According to the standard Big Bang model, these 2 regions have never been in contact. There has not been enough time since the beginning of the universe for light or any kind of influence to travel from one to the other. They are outside each other's light cones, forever isolated by the vastness of space. How then did they manage to agree on the exact same temperature? It is as if you walked into a vast, crowded room where millions of people, who have never met or spoken, are all humming the same note in perfect pitch. This is the horizon problem, and it suggests that the universe in its infancy was far more interconnected than the speed of light should allow. The leading solution is a dramatic one, a concept known as cosmic inflation. This theory proposes that in the first fleeting fraction of a second after the Big Bang, the universe underwent a growth spurt of unimaginable ferocity. A patch of space smaller than a subatomic balloon was stretched to a size larger than our entire observable cosmos in less than a blink of an eye. Before inflation, this tiny region was small enough for every part to be in thermal contact, allowing it to even out its temperature perfectly. Then, inflation took that perfectly balanced microscopic seed and blew it up into the entire cosmos we see today. The uniformity we observe is simply the stretched-out memory of that initial, intimate connection. This paradox forces us to look back to the very first instance of reality, to a time of almost unimaginable energy and violence, to find the reason for the profound calm we see etched across the sky. Our own conscious experience of a single, solid world stands in stark contrast to the ghostly realm of quantum possibilities. The equations work perfectly, predicting probabilities with breathtaking accuracy, but they describe a reality where a particle is a blur of potential locations, a spread-out wave of chance. Then, in an instant, it becomes a single, definite point. The question is, what triggers this shift? What is the magical moment when possibility crystallizes into fact? This is the measurement problem, the deepest and most persistent mystery in all of physics. It is not a flaw in the math, but a chasm between the math and what we actually see. One school of thought places the power directly in the hands of a conscious mind. In this view, the wave function collapses only when it is observed by a conscious being. The universe remains in a state of shimmering potential until a living, aware entity looks at it, forcing it to choose. This idea, while compelling, raises more questions than it answers. What counts as conscious? Does a cat have this power? What about a worm or a single-celled organism? This path leads to a kind of cosmic solipsism, where reality is dependent on mind, a troubling proposition for science. Another perspective argues that collapse is a physical process. It happens when a quantum system interacts with a large, complex measuring device. The trillions of atoms in a Geiger counter or a camera are enough to cause decoherence, a process that effectively destroys the fragile quantum superposition and makes it appear as if a single outcome has been chosen. The problem here is that the device itself is made of quantum particles, so why does it not get caught in the superposition? Where do we draw the line between the quantum and the classical worlds? The most radical solution denies that collapse happens at all. The many worlds interpretation suggests that every possible outcome of a quantum event actually occurs. The wave function never collapses. Instead, the universe continually splits, branching into a near-infinite multiverse where every possibility is realized in its own separate timeline. In this view, you are not a single person but a multitude, living out every possible version of your life. We only perceive one reality because our own consciousness is split along with the universe, forever trapped in a single, linear-seeming branch. So we are left with a profound choice. Is our consciousness a fundamental force that sculpts reality? Is the boundary between the quantum and classical worlds a matter of sheer size and complexity? Or does a vast, unseen multiverse hum just beyond the edge of our perception? The measurement problem is not just about particles in a lab. It asks what we are and what the true nature of our existence might be. The solid world we perceive shatters completely with a simple twist on a classic experiment. A physicist named Lucian Hardy devised a brilliant arrangement that takes the mystery of the double slit and pushes it into the realm of pure logical impossibility. He imagined sending two entangled particles toward two separate double-slit setups. Each particle, on its own, would behave like the particle in the original experiment, showing an interference pattern that suggests it traveled through both slits at once, a ghostly wave of potential. But because these two particles are entangled, their fates are forever linked. The setup is arranged so that if one particle is detected at a specific point, it reveals which path its entangled partner took through its own set of slits. This is where logic breaks. In certain runs of the experiment, you get a result that is utterly nonsensical. You detect one particle in a way that proves its partner must have taken one specific path. Yet at the same instant, the very fact that you got a detection at all also proves that same partner particle could not possibly have taken that path. The particle is caught in a trap of its own making. It must have taken the path, and it simultaneously could not have taken the path. This is Hardy's paradox, a clean, mathematical demonstration that our classical reasoning is built on a foundation of sand. We want to ask, but which way did it really go? The universe's answer is a silent shrug. The question itself is meaningless. A quantum particle does not have a definite path until we force it to declare one. And sometimes, as this paradox shows, we can force it into a declaration that is logically inconsistent. It is as if you asked a friend if they took the bus or the train to work, and their answer was, "I must have taken the bus because you saw me, but I also could not have taken the bus because I am here." The concepts of path and position are not inherent properties of the particle waiting to be discovered. They are stories we tell, narratives that only become real through the specific questions we choose to ask. This contextual nature of reality is the final nail in the coffin for a purely objective, detached cosmos. The universe is not a clockwork mechanism. It is a vast, interconnected network of potential, and we are not just observers but active participants in its unfolding, asking questions that sometimes have no logical answer. A particle's properties might be more like a ghostly accessory than a fixed part of its being. In a stunning variation of quantum experiments, physicists explored a scenario that feels stolen from a fairy tale, the Quantum Cheshire Cat. The name comes from Lewis Carroll's character, the Cheshire Cat, who could fade away until only its grin remained, disembodied and floating in the air. Researchers set up a device called an interferometer, which uses mirrors and beam splitters to create two possible paths for a particle of light, a photon, to travel. This photon is our quantum cat. They then prepared to measure two things: the location of the photon itself and one of its intrinsic properties, its polarization, which you can think of as the direction it vibrates. Through a clever arrangement of measurements, they found something that defies all classical intuition. They could confirm that the photon, the cat, was definitely traveling along one specific path. Yet at the very same time, they could measure its polarization, its grin, as being present and detectable only in the other, empty path. It was as if the smile had been completely peeled away from the cat, existing on its own in a separate corridor of the experiment. This is not a metaphor, it is a result confirmed under strict laboratory conditions. The fundamental quality we associate with the particle was physically separated from the particle itself. This paradox forces a radical question. What is a thing? In our everyday world, we assume an object is a bundle of properties glued together by a substance. An apple is red, round, and sweet, but the Quantum Cheshire Cat experiment suggests that in the foundational layer of reality, this glue might not exist. Properties like spin, polarization, or position may not be inseparable attachments to a tiny lump of matter. They might be more like independent actors that can, under the right conditions, detach and go their own way. The implications ripple outward, challenging the solidity of everything we touch. The chair you are sitting on feels solid and whole, its color and shape seemingly inherent to its material form. But this paradox whispers that this wholeness is an emergent illusion, a convincing magic trick played on a scale our senses can comprehend. At the quantum level, the universe may be a dance of free-floating qualities, and the particles we think of as the dancers might be temporary gatherings of these attributes, not the other way around. Are we and everything we see just a temporary consensus of disembodied smiles? The very freedom to choose our own experiments might be the greatest illusion of all. When a physicist decides to measure a particle's spin in a specific direction, we assume that choice is free and independent, a random variable in the grand equation of the test. But what if that assumption is wrong? What if the scientist's decision is itself a link in a chain of cause and effect that stretches back to the Big Bang, a chain that also predetermined the state of the particle they are about to measure? This is the unsettling hypothesis of super-determinism. It offers a clean, classical solution to the spooky action of entanglement. There is no faster-than-light communication because there is no need for it. The particle and the experimenter were always in sync, their fates woven together from the very beginning of time. The correlation we see is not magic, but simply the result of a shared, pre-written history. This elegantly resolves the quantum paradox, but at a terrifying cost. It shatters the foundation of modern science, which relies on the idea of free, independent choices in our experiments to test reality. If our choices are not free, then every scientific result is suspect. We are not impartial investigators uncovering objective truths. We are simply reading from a script we had no hand in writing, acting out a cosmic play where the ending was fixed before the curtain ever rose. This forces us onto a philosophical tightrope. Do we possess genuine free will, the power to make choices that are truly our own, or are we just sophisticated cogs in a deterministic machine, our sense of agency nothing more than a convincing story our brains tell themselves? The universe, in this view, is a single, unbreakable block where the past, present, and future exist simultaneously. Our journey through it feels real, but every twist and turn was mapped out long ago. Crossing the event horizon of a black hole should be a smooth and silent descent. The sheer force of gravity would be so immense, so perfectly distributed, that you would feel nothing at all as you passed that point of no return. This is the promise of Einstein's equivalence principle, the beautiful idea that a person in freefall cannot distinguish their experience from simply floating in empty space. But our most advanced calculations now suggest a far more violent end. The event horizon may not be a gentle threshold, but a searing wall of high-energy particles, a blazing firewall that would instantly incinerate any matter that comes into contact with it. This is the black hole firewall paradox, a brutal contradiction that pits the core of general relativity directly against the fundamental tenets of quantum mechanics. One theory guarantees a quiet passage, while the other promises a fiery execution. They cannot both be correct. The paradox emerges from the very nature of quantum entanglement. To preserve the information of what falls into a black hole, a concept we explored earlier, the radiation emitted by the black hole must be entangled with the radiation that has already escaped. But for an astronaut falling in, the principles of quantum mechanics demand that the particles just inside the event horizon must also be entangled with those far outside. A fundamental rule of quantum theory states that a particle cannot be maximally entangled with two different systems at once. This creates an impossible choice. To protect the information leaving the black hole, the entanglement must break at the horizon, and that sudden, violent severing of quantum links would release an unimaginable amount of energy, manifesting as the deadly firewall. So you are faced with an impossible scenario. Either you accept the firewall, which incinerates the falling astronaut and violates Einstein's cherished principle of smooth spacetime, or you reject it, which seems to require that quantum information is lost forever, breaking one of the most sacred rules of physics. This is not a minor disagreement. It is a fundamental clash, revealing that our understanding of reality itself becomes incoherent at the most extreme frontiers. The smooth fabric of spacetime and the intricate web of quantum information cannot peacefully coexist at the event horizon. One of them must break. This paradox is a glaring signal, a cosmic alarm bell telling us that our picture of space and time is incomplete. It hints at a deeper, more radical theory of quantum gravity waiting to be found, a theory where the very concepts of inside and outside a black hole may no longer apply. The firewall is not just a threat to a hypothetical astronaut. It is a threat to our entire understanding of the universe, forcing us to tear down our most successful ideas in order to build something new. A simple glass of water holds one of the most stubborn mysteries in all of physics. A Tanzanian student named Erasto Mpemba was making ice cream, and in a hurry, he placed his hot sugary mixture directly into the freezer. To his astonishment, it froze faster than the batches his classmates had prepared with cold liquid. His teachers dismissed the observation as a mistake, a violation of basic common sense. How could hot water possibly freeze before cold water? Yet the Mpemba effect is real, a genuine paradox where a system starting further from its goal somehow reaches it first, defying our intuitive grasp of thermodynamics. The explanation is not simple because the act of freezing is not a single event but a complex dance of many factors. The hotter water loses mass more rapidly through evaporation, leaving less water to freeze. It may contain fewer dissolved gases, which can slightly raise its freezing point. The warmth also sets up powerful convection currents, swirling the water and helping it to shed heat more efficiently into its surroundings. All these processes together can sometimes give the warmer liquid a head start in the race to solidity. This is not just a quirk of water, it is a profound lesson in humility. We often assume that the fundamental laws of physics, like cooling, should operate in a straightforward, linear way. But the Mpemba effect reveals that when these simple laws act within a complex, real-world system, they can interact to produce emergent behaviors that are startling and counterintuitive. The universe is not always obligated to follow our simplest models. It reminds us that extraordinary secrets can be hiding in the most mundane places, in a kitchen freezer, in a steaming cup, waiting for a curious mind to notice the impossible. The final paradox brings us to the very edge of existence itself. Did the cosmos truly have a beginning? The Big Bang model points to a singular, explosive start, a moment of infinite density and temperature where all the known laws of physics simply cease to function. At that point, our most trusted equations dissolve into nonsense. This leads to a question that seems perfectly reasonable, yet might be utterly meaningless. What came before the Big Bang? The problem is that time, as we understand it, may have begun at that very instant. Asking what happened before time began is like asking what lies north of the North Pole. The question itself is a logical trap, a paradox of a beginning that seems to defy the very concept of a beginning. How can something, a universe of staggering complexity and scale, emerge from a state of absolute nothingness, or from a condition where time did not even exist? The human mind recoils at the idea of a creation without a creator, an event without a prior cause. To resolve this, scientists have proposed breathtaking ideas. Perhaps our universe is part of an endless cycle, a cosmic heartbeat of expansion and contraction called the cyclic model, where each Big Bang is both an end and a new beginning. Or maybe the entire cosmos is simply a random quantum fluctuation in a timeless, spaceless void, a single bubble of something that spontaneously appeared in an eternal sea of nothing. Yet these proposals, while elegant, only push the mystery back one step further. If the universe is cyclic, what started the very first cycle? If it is a quantum fluctuation, what are the rules governing the void from which it emerged? The paradox of the beginning forces us to confront the ultimate question and the stark limits of our own comprehension. We are finite beings trying to grasp the infinite, creatures of time trying to understand the moment time was born. Our search for an answer may be the most profound journey we can undertake, a journey that ultimately leads us not just to the origin of the cosmos, but to the very boundaries of what it means to ask a question at all. These 25 cosmic paradoxes are not flaws in the universe's design. They are cracks in our own perception, letting in a sliver of light from a deeper reality. Each one, from the bending of time to the illusion of separation, chips away at our classical, intuitive view of a world built from solid objects moving on a fixed stage. That comforting image is a mirage. The true nature of things is far more fluid and interconnected. Our journey reveals that space and time are not a static backdrop but a dynamic, malleable fabric, woven together in a single entity called space-time. It shows us that the fundamental building blocks of matter are not tiny, solitary marbles but smeared out waves of probability, their existence a shimmering potential until a moment of observation pins them down. And that act of looking is not a passive glance through a window. It is a participatory event, a fundamental force that helps to crystallize reality from a sea of possibilities. These paradoxes are the growing pains of human knowledge. They are the points where our logic, honed for survival in a middle-sized world, collides with the bizarre and beautiful architecture of the cosmos. They do not signal failure. They are invitations to think bigger, to question our most cherished assumptions, and to finally embrace the inherent weirdness that lies at the very heart of nature. This is not a sign of a broken universe, but of a reality far richer and more astonishing than we ever dreamed. Our journey through these 25 cosmic paradoxes has stretched the very fabric of logic, forcing a complete re-evaluation of what we call real. From the deeply personal time of the twin paradox to the unnerving silence of the cosmos in the Fermi Paradox, each contradiction reveals a crack in our classical worldview. Through these fissures, a far more bizarre and wonderful universe shines, one that defies our most basic intuitions about space, time, and our own existence. These paradoxes are not failures of science. On the contrary, they are its greatest triumphs. They are the signposts that guide us away from comfortable falsehoods and toward a more complete and truthful theory of everything. The universe, in its infinite complexity, is under no obligation to make sense to our human minds. Perhaps the greatest mystery of all is that we can comprehend any of it. Let these paradoxes inspire not frustration, but a profound and lasting sense of awe. We would love to hear which of these cosmic puzzles boggled your mind the most. Share your thoughts in the comments below and subscribe for more journeys to the very edge of understanding.